If the altimeter were correctly set to the current altimeter setting and standard atmosphere prevailed, indicated altitude, pressure altitude, density altitude, and the true altitude will all be equal. But since the conditions are always changing and are rarely ever equal to standard atmosphere, we have to figure out these altitudes in different ways to account for these changes. And each type of altitude has its own use and importance. So pilots need to understand what they are and how to obtain them. Indicated altitude is the altitude read directly off the face of the altimeter when the correct altimeter setting is placed in the Colesman window. Pressure altitude is the altitude indicated on the altimeter when 29.902 in inches of mercury, or standard atmosphere, is set in the Colesman window. Pressure altitude is based on standard atmosphere. Remember that the diaphragm inside the altimeter casing is filled and sealed with standard atmosphere. So by setting our altimeter to 29.902, we are checking how far off from this standardized value we are currently at in terms of air pressure. Pressure altitude is extremely important because we use it for a lot of performance calculations, and we use it to determine our true altitude, density altitude, and our true airspeed. Here are two ways to find pressure altitude. The first one is simple and it has already been explained. Set the altimeter to 29.902, and whatever altitude is shown is the current pressure altitude. The other method is to calculate it. So in this situation, let's imagine we don't have an actual altimeter in front of us. We are calculating this before getting into the aircraft. The information we'll start out with is the current altimeter setting and our airport elevation. Here's how to calculate the pressure altitude. Take 29.902, the standard atmosphere value, and subtract the current altimeter setting from it. Multiply this value by 1,000. This is because 1 inch of mercury is roughly equal to 1,000 feet of altitude. Then simply add the airport elevation, or whatever elevation you're currently at, to this number. Here's another example. Density altitude is pressure altitude corrected for non-standard temperature. This altitude is, in basic terms, the altitude at which the current air density matches the standard atmosphere's density for that altitude. In other words, it's the altitude that the airplane thinks it's flying at based on the density of the surrounding air mass. Let's say we're flying and our actual height above sea level, our true altitude, which we will go over next, is 5,000 feet. Remember, this is the altitude we are actually flying above sea level. If the day is hot, has low pressure, and high humidity, our density altitude would be high. So we might be at a density altitude of 7,000 feet. Here, under these conditions, the aircraft thinks it's flying higher at 7,000 feet. So the aircraft performance suffers. If the day is cold, has high pressure, and low humidity, our density altitude would be low. Under these conditions, the aircraft thinks it's flying lower at 3,000 feet. So its performance would be better. Density altitude is the best predictor of aircraft performance. So if we were attempting to take off from a high elevation where the air is already thin on a hot and humid day, we may not even be able to take off because we're at such a high density altitude. The conditions are as if we're at a much higher altitude than we actually are, which makes it difficult or impossible for the aircraft to generate lift. Remember that the aircraft's service ceiling and absolute ceiling are given in terms of density altitude. To find the density altitude using an E6B flight computer, use the right side of the flight computer and line up the pressure altitude with the temperature. Let's say our pressure altitude is 6,000 feet and the temperature is minus 20 degrees Celsius. The density altitude will be displayed here. If a computer is not available, the approximate density altitude can be found using this formula. True altitude is our actual height above sea level. Aviation maps use true altitude, so true altitude is important when considering obstacle clearance. If the altimeter setting was 29.902 and standard atmosphere prevailed, then true altitude would be the same as pressure altitude. But since the conditions are nearly always non-standard, we must correct for non-standard pressure and temperature to give us our actual height above sea level, our true altitude. An important thing to note is that the error is greatest with large differences from standard temperature and with high altitudes above the ground. The less altitude we have above the ground, the less error there will be, even if we are at high indicated altitudes. Also, keep in mind that cold temperatures cause pressure levels to compress, so our indicated altitude must be corrected when the temperature is 0 degrees or less, especially when we are depending on the altimeter for obstacle clearance during instrument flying. Let's find our true altitude using the E6B. Here's some given information. The ground we're flying over is 2,000 feet. Our indicated altitude is 7,000 feet. Our pressure altitude is 8,000 feet. And the outside air temperature is minus 20 degrees Celsius. So sea level is somewhere down here, and we are trying to find out our exact height over it. But since the atmosphere is only present above the ground, and we are concerned with how the changes in temperature in that column of air affects our altitude, we need to isolate it. Figure out our altitude with corrections made within that column of air, and then add the ground elevation back in again. First, we match up our pressure altitude with the outside air temperature on the left side of the E6B. We then take our indicated altitude and subtract the ground elevation, which gives us 5,000 feet. This is our indicated altitude above ground level. Now we look for our indicated altitude on the middle scale, and adjusted for temperature, it's 4,650 feet. To find true altitude, we're not done yet, but we could stop here if we were looking for our absolute altitude, which is our actual height above the ground. We'll go over that next. But to find our true altitude, which once again is our actual height above sea level, we simply add our ground elevation figure to 4,650. So our true altitude ends up being 6,650 feet. Absolute altitude is our actual height above the Earth's surface, with the altimeter correctly set and non-standard temperature is taken into account. Basically, it's the true altitude with the height of the terrain below subtracted out. To calculate it, refer to the previous section explaining how to calculate true altitude, because absolute altitude is obtained in the process. Here's a quick recap of the different types of altitudes and some summarized information about each.